Hi everyone, welcome back. This is Earth and Space Science 102. I'm your instructor, Stephanie Welch, and we're going to continue talking about light today. So we're continuing from the first lectures part of this unit, lecture 17, where we dealt with some of the fundamental aspects of the nature of light and what kind of information that you can determine from light. One of the most crucial things that we covered in that particular lecture was the speed of light. The fact that light travels at a phenomenally fast speed of 300,000 kilometers per second. It's not per hour like you would measure the speed in which you drive down the interstate. This is kilometers per second. So light traveling at that incredibly fast speed can almost feel like it's moving infinitely fast for us here on Earth. But as we'll see in this lecture today, the fact that it's traveling at a particular speed through the immensely huge distances that we have to cover in space means that it's actually going to take light some time to travel. Okay, so that's one of the things that we're going to cover today, is this idea of the relationship between light and distance to the objects, and we're going to get a feeling for just how big and how vast and old the universe actually is. The other thing that we're going to cover is, of course, telescopes. Both telescopes that are capable of seeing essentially in the same spectrum that we use, the visible light spectrum, optical telescopes, versus telescopes that use other wavelengths of light outside the visible light spectrum, other parts of the electromagnetic spectrum, like radio telescopes and telescopes that can essentially see in X-ray, allowing us a different glimpse into the universe. So the first thing that we're going to get into, going back to this relationship between the speed of light and distances, is this concept of a light year. This is really, really important for everything else that we talk about in this unit, because it's a really perfect unit of distance when you're talking about distances outside of our own solar system. So on the Earth's surface, we can talk about distances in terms of kilometers or miles, or maybe even feet and meters. Relatively short distances are relatively easy to talk about using these units because the numbers stay pretty small. Even if we're talking about the distance from Los Angeles to New York City in terms of kilometers or miles, that's still a relatively small number. When we look out into space, those numbers get to be really, really big because space is a big, big place. Even the distance between us and the sun, a relatively short distance compared to other distances that we're going to talk about, is 150 million kilometers. So when you start getting into numbers that big, you have to add so many zeros to something to make it fathomable that that number almost becomes meaningless. The difference between millions and billions and trillions becomes almost seemingly nuanced in comparison. So our unit of distance, when we get outside of our own solar system, is going to be the light year. 1 light year is the distance that light can travel in a year, traveling at 300,000 kilometers per second. So if light can travel 300,000 kilometers per second, think about how much of a distance it can take in a minute, 60 times that. How long of a distance can light travel in an hour, in a day, in a year? The equivalent of 1 light year in terms of kilometers is 9.46 trillion kilometers. That's how far light can travel in a year. And you'd almost want to think that a number like trillions of kilometers would take you from one edge of the universe to the other edge of the universe, but it's not even close. It's not even approaching the right order of magnitude for the kind of distances that we have to talk about, which is why this idea of a light year is so crucial. Now, to relate this to a unit of distance that we've already talked about, the astronomical unit, our unit of distance for the solar system unit, the idea of 1 astronomical unit is to compare everything back to the average distance between Earth and the Sun. 1 AU is effectively 150 million kilometers. That would be the equivalent of not light years, but light minutes. The sun is 8.3 light minutes away. It would still be an incredibly short distance in terms of light years. So Earth to the moon in comparison is 1.3 light seconds away. It takes 1.3 seconds at light traveling at 300,000 kilometers per second to travel from the light, have light reflected off of the moon and reach us here on Earth. So you can almost think about any of these distances in terms of the relationship with light as having a little bit of a time delay. There's a 1.3 second time delay for the light to reach us from the surface of the moon. There's an 8.3 minute time delay for light to reach us from the sun. So, just as an exercise, what if somebody went and switched off the sun? If some great deity out there in the cosmos just turned the sun off? It would take 8.3 minutes for us to be aware that the sun no longer worked. It would take time because light takes time to travel across space. Light does travel at a finite speed. And the greater the distance that you're talking about, the more apparent this becomes. When you get outside of our own solar system to the nearest neighboring solar system, the nearest neighboring star, the distance becomes 4.4 light years. That's the distance from us to the nearest star called Alpha Centauri. The nearest globular cluster, it's these gravity-packed balls of stars that kind of float in and out of the Milky Way galaxy, is 25,000 light years away. The distance to one of the closer galaxies, the Andromeda galaxy, is 2.5 million light years away. So particularly when you get first outside of our own solar system and then outside of our own galaxy, these distances really, really start to add up. So what I want to do with you now is to let you kind of explore this idea of a time delay between the light reaching us from the sun and from distant stars and from distant nebulas and so on. Let you explore this idea a little bit more by showing you a clip from the 2014 series Cosmos, sort of the reboot of Cosmos from the 1980 version with Carl Sagan. This one hosts Neil deGrasse Tyson, of course, and he's going to kind of take you on an increasing distance exploration of how this relationship between light and distance works. So I hope you enjoy it. So Neil deGrasse Tyson took us a lot further than I did when I was telling you about this relationship between light and distance. He took you to the edge of what we call the observable universe. So the universe itself might actually be infinite. We don't know, because there is a wall that we can't seem to get past, because to look past that wall would be to look past the beginning of time, to look back to a time before the universe actually formed. So because of this time delay and because of the immense, unfathomable distances that light has to travel, as you look further and further and further away from our planet, you go further and further back in time. So this is a really, really incredible thing for us, because you could almost see it as a disadvantage. We're not seeing things as they actually are. We're seeing things as they were. But without this, we wouldn't be able to effectively time travel. We wouldn't be able to look at a distant galaxy or even that cosmic microwave background radiation from the Big Bang and understand some of the earlier steps in the formation of our universe. So while we can't see these really, really distant objects as they currently are, we can see them as they were and get an idea of the history of the universe. So that's the really sort of big, profound thought for the day. Because of the amount of time it takes for light to reach us, the further we look out in distance, the further we look back in time. To look at something 2 million light years away is to time travel 2 million years into the past. To look at something 13.7 billion light years away is to look back to the moment of the Big Bang and the origin of the universe itself. So as a little bit of a thought experiment, let's turn around the tables on this. We've thought about everything from our point of view, from our position here on Earth, looking out into the cosmos, looking out beyond our own solar system, and thinking about how we're looking backwards in time. I want to introduce this idea that for somebody else, some alien civilization, hypothetical alien civilization in another galaxy, the same thing would be happening to them. So as a little bit of a thought experiment, let's think about some hypothetical planet a hypothetical solar system in the Virgo cluster of galaxies. That's 65 million light years away from Earth and our local group of galaxies. So as that alien civilization looks outwards, and let's assume that they are incredibly advanced and build telescopes the likes of which we would never be able to invent here on the Earth's surface. Let's say that they could point their telescope anywhere out there in the cosmos and not just see individual stars and galaxies, but even be able to detect planets. And for us, this would be, of course, impossible. And let's say that alien civilization, 65 million light years away, decides to turn their telescope to Earth. The question is, would they see us? Would they see human beings walking around on the surface of the planet? The answer to that would be, as far as we understand the nature of light to work, the answer would be no. They would not see humans because humans would not evolve for another 60 million years. If this hypothetical planet were actually 65 million light years away, and because of that time delay that we've been talking about this whole time, as they train their telescope on Earth, they would see the catastrophic event at the end of the Cretaceous period. They would see a massive, massive asteroid hitting the modern day Gulf of Mexico, creating that Chicxulub impact crater. And they would see essentially the death of the dinosaurs. An even more distant civilization wouldn't even be able to see dinosaurs. They wouldn't even be able to see any type of life on the surface at all. They would only see, be able to perceive maybe marine life on Earth. So there is a limit, again, to how far away we can see, because as we go backwards in time, we go back to the very beginning. Using the rate in which the galaxies expand away from each other and using this distance that you can calculate based on the total distance that we can see away from us in space, you can get an idea of not just how big the universe is, but how old it is. And while it might be far larger than this, because we're not situated at the very center, there is an edge to the observable universe, and that's 13.7 billion light years in any direction. Take your telescope out, point it in any direction, and I say take your telescope out. You'd actually have to be looking at the Hubble telescope or something even more sufficiently advanced to be able to detect this very, very, very most distant light. Point your Hubble telescope in any direction and you can only ever see 13.7 billion light years away from Earth because you're looking all the way back to the very beginning. All right, so that segues us out of this relationship between the nature of distance and light and a light year, what that's all about, to telescopes themselves. Telescopes are incredibly important tools for astronomy. And without these telescopes, we would know very, very little about even our own solar system and virtually nothing about more distant objects. So remember, it was when Josef Fraunhofer combined not only just having the prism, but the prism with the telescope, that allowed us to understand the composition of objects. That allowed us to see what we now call Fraunhofer lines and to understand an object's composition. So having a telescope is a really, really crucial tool in all of this. And I wanted to first kind of go over some basic aspects of telescopes, why they're useful, why they allow us to see things essentially better than our eyes can, before I get into different types of telescopes and telescopes on the Earth's surface versus out in a low Earth orbit. So what makes a telescope useful is not necessarily its magnification. That's just how people like to sell you on telescopes. If somebody's trying to sell you a telescope, they might tell you that it has this amazing magnification. But if you're dealing with a relatively small telescope, its power in allowing you to see things in a greater detail is still going to be fairly diminished, because the most important thing that a telescope can do is to collect more light than your eyes can. And to do that, telescopes have to be really big. That's why big research telescopes are enormous. 20 and 30 meter lenses that are concentrating light down to your eyepiece, as opposed to some backyard telescope that might have an overall light collecting area of about that big, maybe inches across. So bigger is better in terms of telescopes. A telescope being able to capture more light than your eye can is all about having a bigger light collecting area than you do. And your personal light collecting area is the pupil in your eye, the little black part in the very center of your eye. That's your capacity for detecting light personally. That's why your pupils get bigger at night. If you go outside at night, your pupils get a little bit larger. They get a little bit smaller if maybe you're under bright lights like I am right now. Your eyes are adjusting to the amount of light that they're taking in so that they can see things in as much detail as possible. Particularly to see things at night and to see things outside of our own solar system, so beyond the sun and the moon, you need to be able to collect as much light as possible. Now, the secondary power of a telescope, the secondary importance, is not only to be able to collect more light, but to then focus that light. And that's where mirrors and lenses come in that allow you to see things in a greater detail and allow you to focus that light down to the eyepiece. So the resolving power is all about having the lenses and the magnification. The focusing power is about having those lenses and mirrors concentrate the light down to your eye. And different telescopes do this in different ways. This light gathering power is going to be a function of the collection area, first off. So how big an area you have to take in light. Just like a bigger bucket might be capable of collecting more rain than a smaller bucket, a bigger telescope can collect more light than a smaller telescope can. So bigger is better again. That's why these telescopes called reflecting telescopes end up being better, because these reflecting telescopes end up being able to bounce more light around and get it down to your eyepiece more than what we call refracting telescopes. I'll get into that in just a second. So having the big light collecting area, that's really important, but even more important ends up being taking that light and being able to actually concentrate it on a very, very, very small point. So all that light, anywhere between maybe inches to feet to meters of light collected in this bucket, essentially determined by the size of that telescope, has to get down to a single point, and that's your pupil. That's one tiny little area. So it has to be able to be focused. Okay, so your basic optical telescope design is either in refracting telescopes, that still have their uses today, but fewer than they had in the past, versus reflecting telescopes. In terms of being able to collect a lot of light, for reasons we'll get into in just a minute, reflecting telescopes are a little bit better at that. But what refracting telescopes do, first off, is take light from a distant object and bend that light down to the eyepiece. In order to take something like light and to bend it, that light has to be passed through something like a curved piece of glass, a lens. Just like a hand lens, or even maybe the lenses in your glasses or contacts, that is going to bend the light down to your eyepiece. So refracting telescopes, both for reasons of economy and for practicality, end up not having the same sort of light collecting area that reflecting telescopes do, because lenses are really expensive to manufacture, and a really huge lens for a big light collecting area would be extremely expensive. So refracting telescopes today end up being used more for objects that already create a whole lot of their own light. So for studying, say for instance, the sun, the moon, features relatively close planets like Mars and Venus. You don't really need much more than a refracting telescope that might not collect that much light, but might allow you a lot of magnification. The very first refracting telescope was also really sort of the first telescope overall. The first of the more famous Renaissance scientists to actually look through a telescope was Galileo, with his very, very, very funky little refracting telescope. Had something like a 3 times magnification, but because he was the first one to be able to look out into space through a telescope, like this. He was able to see phases of Venus, moons surrounding and orbiting Jupiter, spots on the sun, and so on. He was able to pick out all of these little sort of nuanced imperfections that allowed us to come up with this idea that objects orbiting around our sun, it's not really as big of a deal as was previously thought. And he came up with this in part because he had the telescope, he had the tool. Now, refracting telescopes use only the lenses, and those lenses bend the light down to the eyepiece. Reflecting telescopes ultimately accomplish the same goal, but can utilize a lot more light coming down to the eyepiece, because you can essentially have a bigger bucket, a bigger light collecting area. Light can be collected across a much, much bigger swath of surface and then bounced down to your eyepiece through a series of lenses, through primary and secondary, not lenses, mirrors. So that's why it's a reflecting telescope as opposed to refracting. The refracting telescopes are bending the light in. Reflecting telescopes are allowing that light to be reflected off of the surface of mirrors. And the orientation of those mirrors is set up to concentrate that light again down to your eyepiece. So it'd be really dangerous. It's already very dangerous to stare directly into the sun. It would be even more dangerous to point one of these reflecting telescopes towards the sun, or even maybe towards the surface of the moon, through objects that are already producing a whole lot of light. But when you look at distant stars and distant galaxies, they're not so much producing so much light. It's still safe at this point to point one of these reflecting telescopes at some of those objects, those more distant objects. Now, the Keck telescopes, the ones on top of Mauna Kea, the big island of Hawaii, most of the ground-based observatory telescopes, even the Baton Rouge Observatory on Highland Road, just south of the main sort of central part of the LSU campus and so on, those are all reflecting telescopes. You have a lot of light collected, bounced around through the series of mirrors down to your eyepiece, and then you can see things in an enormous amount of detail. In terms of how much light you're collecting, definitely better than the refractors. For most objects that we care about and objects that are distant in space, also better than the refractors. Newton actually had the first reflecting telescope, the telescope that allowed for more light to be collected. And so it's not just a matter of brain power that allowed some of these really famous Renaissance and later scientists to do what they did. It was a question of having the right tool for the job. Now, the right tool for the job in modern day astronomy involves not really spending so much time looking directly into a telescope, but allowing the computer to do the same thing. So most research astronomers today are not looking directly into telescopes. They're looking at computer screens and bringing up these images generated by telescopes. Some of those telescopes might not even be on the ground surface, although some of them still are. Some of these telescopes might be out in space, out in orbit around Earth. And the likely thinking here is that the reason why an astronomer might want to stick a telescope into Earth's orbit is to get it closer to the stars. But the first thing I want to kind of disabuse you of is that notion that actually taking a telescope and putting it into orbit around Earth gets you appreciably closer to stars. Taking a telescope and putting it into orbit to get it closer to the stars is like taking one step out of the building to get closer to New York City. It's such a marginal, very, very, very small distance compared to the total distance that you've got to cover that it doesn't make a real difference. So we don't put telescopes into space to get them closer to the stars, not appreciably so anyway. We put telescopes like the Hubble telescope, the James Webb Space Telescope, the Chandra Observatory, and others. We put these telescopes in orbit for other reasons. And we'll go through these. There are three main reasons why we put telescopes into space. The first, and the one that the ancient Greeks and even the Renaissance scientists didn't have to contend with, is the light pollution on the Earth's surface. In the 20th and 21st century, we've gone a long way to lighting up the night sky from the perspective of the Earth's surface. We have produced so much light on the Earth's surface that if you were, like Carl Sagan and Neil deGrasse Tyson, if you grew up in New York City, I can't believe that those people ever even got into the subject of astronomy, because they could look up in the night sky and barely see any stars at all. Even for somebody growing up in a fairly rural area. I grew up way, way north of Covington, Louisiana, way out in the middle of nowhere. Even I didn't have as unimpeded of a view of the night sky as I wanted to think I did as a kid. In order to get to a place on Earth where you have a completely unimpeded view of the night sky and you see the same night sky that maybe the Greeks did and the Renaissance scientists did, you'd have to go to some incredibly remote corner of the globe. You'd have to go out into maybe the Amazon rainforest or the Congo or Antarctica. You'd have to go somewhere incredibly remote. And most research observatories that are located on the Earth's surface have to balance this, necessity of getting far enough away from a populated city to get away from the light pollution, but they have to balance that against people actually being able to get there, because it's going to be a lot more difficult to get people to a research telescope on Antarctica than it is the Lowell Observatory in Arizona, for instance. So this map really shows you, and this is a wonderful thing created by the National Geographic magazine. This shows you how pervasive light pollution is across the entire globe, across all of the continents. Nowhere in North America, even my little rural upbringing north of Covington, is unimpeded by this issue of light pollution. No view that you've probably ever had in your life of the night sky has been as complete as the ancient Greeks and the Renaissance and all of the early people of the earth were able to have. So it gives you a little bit more of an appreciation probably for how devoted they were to understanding and studying the night sky, because they were able to see it a lot better than we were. Now, taking us back to the main point here, the reason why this is important for the subject right now is because getting a telescope into even low Earth orbit, where you're almost not even completely out of the Earth's atmosphere yet, that takes you away from all of that. You don't have to contend with light pollution when you have a telescope in even low Earth orbit, much less even maybe a distant orbit. The second thing that you have to contend with a ground-based telescope versus a telescope in Earth's orbit is the twinkling that happens with stars. One of the really easy ways to discern the difference between a planet and a star, whether or not you might be looking at Venus or maybe a really bright distant star, is whether or not that object's light actually twinkles. And the twinkling has really nothing to do with the light coming from the object. It has to do with what happens to that light when it moves through the Earth's atmosphere. So planets don't twinkle as much because they're reflecting light from the sun, and because they're relatively close to us, they're a little bit more higher powered. So that's one way of discerning the difference between the two. Light from stars definitely twinkles, but the actual power that a star emanates, the amount of energy and light that a star emanates, does not twinkle. It doesn't fade with time. All stars in the night sky are supposed to be essentially like our sun and produce a constant amount of light, like light from a light bulb instead of a weak and dim and dying flashlight. So light from stars, and any other object actually, has to get through the Earth's atmosphere. And having light travel through the Earth's atmosphere, effectively for us with ground-based telescopes, ends up being fairly similar to sitting maybe on the bottom of a swimming pool with your goggles and looking up and seeing the light have to move through the water. Having light have to move through the Earth's atmosphere as having to move through a material that's always constantly shifting, all this moisture in the atmosphere, the actual air in the atmosphere. It doesn't stay still. It's constantly moving around as the wind blows and clouds develop and so on. So that light has to make its way through this ever-shifting atmosphere, and it essentially scintillates, or it twinkles when we finally are able to perceive that light from our position on the surface of the Earth. So the picture over on the left shows you a still image of the light from a distant star. Very poorly resolved, really grainy, terrible picture with a ground-based telescope, because in part of that issue of having that light have to travel through the Earth's atmosphere. In comparison, light from a telescope in orbit is not going to do the same thing. It's not going to blur in the same way because there's nothing to blur that image. The light doesn't have to travel through the gas of the Earth's atmosphere to reach us here on the surface. It instead only has to get as far as, let's say, the Hubble telescope or one of the other major telescopes out in orbit. Now, the third reason probably is the most important reason. Our atmosphere is really, really effective at blocking certain wavelengths of the electromagnetic spectrum. And that's a really good thing for almost everybody but astronomers. And even to a certain extent from the astronomers, from the standpoint of, them being able to live out their lives on the Earth's surface. The exact composition of the gas in the Earth's atmosphere does a really, really effective job at blocking out most of the shorter wavelengths of the electromagnetic spectrum. So as you can see, the gamma rays, the X-rays, most of the UV spectrum is entirely blocked by the Earth's atmosphere. So if we want to study those wavelengths of light, we have to get away from the Earth's surface and out of the Earth's atmosphere and into outer space to be able to do so. And therefore, the observatories that capture those wavelengths can only do their job from Earth's orbit. Even the longer wavelengths of the electromagnetic spectrum, some of the radio waves and some of the infrared waves can't get down to the Earth's surface. So in effect, the only research telescopes that are on the Earth's surface and can really do their job are regular optical telescopes capturing visible light, like most of the research observatories out there, and radio telescopes, because long wavelength radio waves also are able to penetrate the Earth's atmosphere. Effectively, everything else requires us to stick that observatory and stick that telescope out into space. So these non-visible wavelengths are really, really crucial for understanding some of the most mysterious and unknown things that are going on in the universe. Sure, we can study a star. We can even maybe study certain types of nebula and certain other really hot objects just through optical light. But in order to understand what's going on in a black hole's accretionary disk, neutron stars, certain types of nebulas, what happens and what gets created when black holes and neutron stars collide with each other and so on. In order to really see those things, you need non-visible wavelengths of light. So cold gas clouds, for instance, the colder nebulas, are invisible in terms of the visible light spectrum, but they create radio waves. They're visible in radio waves. The dust clouds that compose most of the Milky Way galaxy would be impenetrable without these other wavelengths of light. We can see what's going on better in the infrared part of the spectrum. X-rays allow us to see accretionary disks around black holes and so on. We wouldn't be able to detect neutron stars at all without X-rays. We wouldn't be able to have observed neutron stars to begin with without radio waves, and the fact that they pulse radio waves. So much of the universe would remain invisible to us if we were not able to detect these alternative wavelengths of the electromagnetic spectrum beyond visible light. So I wanted to tell you a little bit about some of these telescopes that are actually out in Earth's orbit, that are either in low Earth orbit, or sometimes they're even further away from the surface of our planet, well out of the effect of the Earth's atmosphere. The most famous of all of these, the one that you've almost certainly heard of before, is the Hubble telescope. And the Hubble telescope does utilize other wavelengths of light beyond the visible light spectrum. It also captures radio waves, but it effectively does everything that a ground-based telescope can do, only better. So it's been up there for a fairly long time. It's been up there since the earliest part of the 21st century, the early 2000s. So it's really almost sort of nearing the end of its useful lifespan. It's soon to be replaced by the James Webb telescope. The Hubble telescope is in low Earth orbit, and it just really sort of allows us to do everything that we could do on the surface of the Earth, but only better. The Hubble telescope's probably greatest achievement is definitely popularizing astronomy. There's some of the amazing, amazing pictures that it's been able to generate that are far, far greater than anything that we could create on the Earth's surface. Now, all of these other telescopes beyond the Hubble telescope are capturing other wavelengths of light. Like take, for instance, the EUVE, the Extreme Ultraviolet Explorer. It captures, of course, UV light. That same wavelength of light of the electromagnetic spectrum would barbecue you and immediately plunge you into miserable, miserable skin cancers if that light was actually capable of making its way through the atmosphere of Earth and to the Earth's surface. But it doesn't do this. It isn't able to penetrate through the Earth's atmosphere, and instead we have to stick that telescope up into orbit to be able to capture that light. And that light allows us to be able to understand things like stars even better than we can through visible light alone. The infrared space telescope, the Spitzer infrared space telescope, allows us to see essentially the heat coming off of objects, which is all infrared light really is. It's the heat coming off of objects. And then finally, the Chandra X-ray telescope, also up there in orbit, also capturing a different wavelength of light than we can on the Earth's surface. Finally, I wanted to sort of close on this new telescope that isn't actually up there yet. It's planned for 2018 and is very, very much in many ways the successor of the Hubble telescope. Even while it'll work mainly in the infrared part of the spectrum, it's going to be also capable of producing optical telescope pictures, and it's going to be far, far larger, have a much, much greater light collecting area, and it's going to allow us to understand the early part of the universe far, far better than we are currently capable of through mainly the Hubble telescope alone. So this is, of course, the James Webb Space Telescope. Only a couple short years from now, it's going to be up there in space at the second Lagrangian point. So basically, this means that it's going to be positioned much further away from the surface of the Earth than the Hubble telescope is. The Hubble telescope is in low Earth orbit, so just sort of barely right on the edge of the Earth's atmosphere. The James Webb telescope is actually going to be further away from the Earth than the Moon is. But that increase in distance, again, doesn't really get you appreciably closer to the objects that it's hoping to observe. What it's really going to do is just allow for a more stable view of these more distant objects. And so that's a really cool event that's sort of on the frontier for NASA and for astronomy in general. All right, so that's going to conclude our whole discussion of the nature of light and distance and telescopes. And from here on out, we'll really be able to talk specifically about stars. First, one star in particular, we're going to talk in detail about our star, our sun, because understanding what's going on with our sun is the greatest tool that we have for understanding what's going on with more distant stars. We effectively know this one better because we happen to just be right on top of it, not because it's particularly important, only for us. We'll then go from talking about our star to classifying other types of stars and to be able to look at their whole lifespan from birth to death, essentially. So I'm very excited to be bringing you the next few lectures really soon. Until next time, keep looking up.